This is the video. In this one, I am discussing differentiability. This differentiability, before this continuity, without disturbing the definitions of continuity and differentiability from mathematical analysis, just we have developed in this video nice strategies to solve the problems of mains and advanced level. So it is problem solving strategy for the continuity and the differentiability. Let me call it to be the JE Technique 2 in our series. So this process, that is divided into some cases. So the case one is that about the continuity and the differentiability. Continuity or the differentiability is a property of a function at a point, a real valued function which is defined on a real line at a point in this case. So here, if a function is continuous at every point in that interval, then we say that the function is continuous on that interval. If the function is differentiable at every point in that interval, we say that it is a differentiable in that interval. So first of all, geometrical meaning of continuity is that when you trace its graph, there are no breaks in its graph. So continuity at a point means is that at that point, the graph has no break at all. And the differentiability geometrical meaning is that the function is said to be differentiable at a point. At that point, curve is smooth. That is, there are no peaks or sharp edges on the curve. Or at that point, unique tangent can be drawn to that curve. So that is the geometrical meaning of differentiability. Let us start with problems. Slowly from problems, we will go to the general case. Let me discuss if fx is x cube minus 3x square plus x plus 5, if x is less than 2. And is 2 cos pi x plus x square by 2 minus x plus 2, if x is greater than 2. And at 2, the function value is 3. This is the way the function is given. Its meaning is that if you write in piecewise form, it will become like this. If x less than 2, it is x cube minus 3x square plus x plus 5. When x is equal to 2, its value is 3. If x is greater than 2, it is cos pi x plus x square by 2 minus x plus 2. For such this function, I am checking the continuity and differentiability at the point x is equal to 2. So when a problem is given like that, if we take the interval like this, and this is the point at x is equal to 2. So for this interval, left side, right side, all right. If we evaluate like this, then evaluations becomes easy, or checking becomes very easy. So at 2, function value is 3. Let us write like that. Then limit as x tends to 2 minus, means at x is equal to 2, left limit, as the x is tending to 2 through the left limit. Then in the left side of 2, the piece of the function is x cube minus 3x square plus x plus 5, which is evaluated at x is equal to 2. This value simplified, I got it to be the 3, but this is same as the f of 2. Means a to 2, the function value which is 3, which is the same as the left limit of the function a to 2. Therefore, we say that at this stage, it is the left continuous a to 2. And limit as x tends to 2 plus a to 2, I am evaluating the right limit. In the right side of 2, the function formula is given by cos pi x plus x square by 2 minus x plus 2. When it is evaluated at x is equal to 2, this also I got it to be 3, which is equal to value of 2. Means here also, the value of the function at 2, which is 3, is same as the right limit of the function at 2. because the right limit is equal to the value of the function. It is a right continuous at x is equal to 2. So it is left continuous at x is equal to 2 and also right continuous at x is equal to 2. So overall it is continuous at x is equal to 2. At the point x is equal to 2, it is continuous. So continuity is very much clear. Now let me check the derivative. At 2 left derivative, which is f dash of 2 minus. You observe that in the left side of 2, so the derivatives I am writing in the down of the line. Function I am writing in the above. When you write its derivative, 3x square minus 6x plus 1, that is the derivative function. That derivative function evaluated at 2, so its value is 1. That implies that left derivative of f at 2 is 1. Similarly, right derivative of f at 2, in the right side of 2, function's derivative is minus pi sin pi x plus x minus 1, evaluated at x is equal to 2. This is also 1. So left derivative is equal to the right derivative. Therefore, the function f of x is differentiable at x is equal to 2. And that common value, that is 1, is exactly the derivative of f at 2. That is f dash 2 is equal to 1. So for the case 1, that is at a point, left side given by one formula, right side given by one formula. For such a function, continuity and differentiability will go like this. This is one of the case. Let us see the case 2. Case 2 also, I am discussing with a problem. F of x is equal to sine inverse of sine x at odd multiples of pi by 2. You can see that for this function, domain is the full real line. At every x, it can be defined. So, but at the odd multiples of pi by 2, I want to check its continuity and differentiability, right? So now, sine inverse of sine x is nothing but minus 1 to the power n into x minus n pi, when x is in between n pi minus pi by 2 to n pi plus pi by 2, when n is any integer. When n is any integer, that formula holds exactly like that. That is a simple observation from inverse trigonometric functions. So that f of x piecewise, if you write it, I am checking that continuity, differentiability at 2 points. One is pi by 2, other is 3 pi by 2. So in between minus pi by 2 to plus pi by 2, function is nothing but the x only. In between pi by 2 to 3 pi by 2, it is pi minus x. In between 3 pi by 2 to 5 pi by 2, it is x minus 2 pi. So draw the line like this. This is pi by 2 and that is 3 pi by 2. Now, at pi by 2, I am calculating the left limit. Pi by 2 limit as extends to pi by 2 minus. In the left side of pi by 2, the function is given by the x. That x is evaluated at pi by 2. I got its value is pi by 2. Means at pi by 2, left limit is pi by 2. I got it. Similarly, for the same function, at pi by 2, right limit I am calculating. In the right side of pi by 2, function formula is given by pi minus x. That pi minus x evaluated at pi by 2, I got it to be pi minus pi by 2 is again pi by 2. So that implies that here the left limit at pi by 2 and the right limit at pi by 2, both of them are equal, which is same as the value of the function at pi by 2. Therefore, it is continuous at pi by 2. And at 3 pi by 2, I am checking. At 3 pi by 2 left limit given by the formula pi minus x, which is evaluated at 3 pi by 2, then pi minus 3 pi by 2, which is minus pi by 2. So the left limit at 3 pi by 2 is minus pi by 2. Similarly, right limit at 3 pi by 2 I am calculating. So right side formula is x minus 2 pi. When it is evaluated at x is equal to 3 pi by 2, that is 3 pi by 2 minus 2 pi is again minus pi by 2. So here also yet 3 pi by 2, left limit is minus pi by 2 and right limit is also minus pi by 2. So therefore it is continuous yet 3 pi by 2 also. So at odd multiples of pi by 2, this function is continuous. Let me check its differentiability. Now you see in the same above line, in the left side of pi by 2, you observe here in the below part I am writing. In the below part I am writing that is the derivative of x, which is 1. So therefore the left derivative at pi by 2, that is f dash pi by 2 minus left derivative at pi by 2 is nothing but the 1, right? And the right derivative of the pi by 2 is given by the formula derivative of pi minus x, which is minus 1. Therefore right derivative at pi by 2 is minus 1. Here at pi by 2, left derivative is plus 1, right derivative is minus 1. Therefore the function is not differentiable at pi by 2. Let us check at 3 pi by 2. For the 3 pi by 2 in the left side, derivative formula is minus 1. Therefore f dash of 3 pi by 2 minus 1 is nothing but the minus 1. That is left derivative of f at 3 pi by 2, which is minus 1. And in the right side of 3 pi by 2, the derivative formula is given by 1. Therefore its right derivative at 3 pi by 2 is plus 1. So here again at 3 pi by 2, left derivative is minus 1, right derivative is plus 1. Therefore it is not differentiable at 3 pi by 2. Therefore this function at odd multiples of pi by 2, it is continuous but not differentiable. Why it is? Because like this, let us see its graph. That is y is equal to fx is equal to sine inverse of sine x. Some pieces in that interval I am writing. When x is from minus pi by 2 to pi by 2, it is x. When x is in between pi by 2 to 3 pi by 2, pi minus x. When x is 3 pi by 2 to 5 by 2, pi minus 2x, it is like that. Like that above also, that function we know from its definition. So those points, let us try to trace its graph. So this is x-axis, this is y-axis, and this is the origin. This point is pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2. And this is minus pi by 2. When you observe that in the interval minus pi by 2 to plus pi by 2, it is y is equal to x function. So y is equal to x graph is like this in the interval minus pi by 2 to plus pi by 2. Now in the interval pi by 2 to 3 pi by 2, it is like this. This graph is y is equal to pi minus x. You can observe here at pi by 2, this point, this circled point, the graph has no break, but at that point sharp edge is formed. One peak, one sharp edge is formed. Means at that point the curve is not smooth. Means at that point tangent is not unique. Therefore it is not differentiable at pi by 2. Similarly, from 3 pi by 2 to 5 pi by 2, the piece of the function is y is equal to x minus 2 pi. Again at 3 pi by 2, sharp edge is formed. There is no break in its graph. It is continuous because a sharp edge is formed. Peak is formed. Therefore, it is not smooth. Therefore, not differentiable at 3 pi by 2. Similarly, in between 5 pi by 2 to 7 pi by 2, 3 pi minus x, yet 5 pi by 2, again it is not differentiable. Yet 7 pi by 2 also not differentiable. Yet minus pi by 2 also not differentiable. That is, the curve is continuous everywhere, even at odd multiples of pi by 2 also, but not differentiable at odd multiples of pi by 2. At all other points, it is differentiable. yet only odd multiples of pi by 2, it is not differentiable and continuous everywhere. So therefore, this is the example which is continuous but not differentiable, right? Now let us see one more problem. This is a previous IIT JEE problem connected to case 3. F of x is equal to x minus 1 whole to the power m into sine of 1 by x. All right. And here x domain is again full real line except at 1, because at x is equal to 1 it is not defined in that formula, but at x is equal to 1 he is defined as the 0. The function is given like that. Therefore, its domain is full real line, right? Then what is the range of m? That is, what are the different values of m so that different conditions? First one, if f of x is continuous at x is equal to 1, what must be the range of m? When fx is continuous, means as x tends to 1 plus or 1 minus, x is tending to 1 through the left side or right side, then x minus 1 will be tending to 0 plus or 0 minus. Therefore, 1 by x minus 1 tends to either plus infinity or minus infinity. Once 1 by x minus 1 tends to plus minus infinity, then sign of that value always lies in between minus 1 and plus 1, but very fastly oscillates in between minus 1 to plus 1. So sine of 1 by x minus 1 oscillates in between minus 1 to plus 1. But the second part, when you observe, as the x tends to 1 plus or 1 minus, then x minus 1 always in between minus 1 and plus 1. So now I am expecting, because the above PC is oscillating in between minus 1 to plus 1 very fast, as this limit must be equal to the value of the function which is 0, which is given there, it should happen that x minus 1 whole to the power m should tend to 0. Then only the function becomes continuous. Once x minus 1 tends to 0 is possible when m is a positive number. Therefore, the range of m is from 0 to infinity. As the m is from 0 to infinity, then the f of x function is continuous at x is equal to 1. Now, the second part is that we are expecting that f of x is differentiable at x is equal to 1. So, for the differentiability at x is equal to 1, sometimes checking the differentiability, it becomes very much convenient when we come through the first principles. When we come through the first principles, checking calculations becomes very easy. Here, I am checking through the first principles. Limit as x tends to 1, fx minus f1 by x minus 1 is the derivative of f at 1. So this thing I am calculating for this function. F of x is nothing but x minus 1 to the power m into sine of 1 by x minus 1, and f of 1 is nothing but the 0 by x minus 1. But you check this. This below x minus 1, when you take it up, it becomes x minus 1 to the power m minus 1 sine of 1 by x minus 1. For the differentiability, we are expecting that this limit should exist. For the differentiability, for the existence of differentiability, this limit should exist. This limit exists from above argument. In the above argument of continuity, m role is played by m minus 1 here. Therefore, it will happen that m minus 1 must be positive. Therefore, m must be greater than 1, means m must be in the interval 1 to infinity open. So when m is from 1 to infinity, then the function is differentiable at x is equal to 1. Now the third one is that f of x is continuous but not differentiable, we are expecting. It is continuous. Therefore, from the first part of the problem, m must be there from 0 to infinity. And it is non-differentiable, we are expecting From the second part of the problem, m should not be there in between 1 to infinity. When we mix up these two things together, m must be there from 0 to 1. 1 is closed, 0 is open. These are the different ranges of the m for different requirements of that function f of x. All right. And this is previous IIT JEE problem. Right. This is very important. And not only this, it's a concept. This concept is also very important. Now let us see the case 3 now. The function is given in this form. When f of x is given by the piece g of x, when x is not equal to a. Except at a, function f of x is given by the piece g of x, and at x is equal to a, function value is given by the k. For such this function, at x is equal to a, I want to check its continuity and differentiability. So the solution, so f of x is piecewise given like this. So x-axis, y-axis, at x is equal to a. If x is less than a, means in the left side of a, function is given by the g of x. So its graph is like this. Yet x is equal to a, which is not included in this piece. So this formula is y is equal to g of x. Yet x is equal to a, that function has the whole for that function g of x piece. Right. Therefore, I am denoting with a small hole there, small circle there. And at x is equal to a, function value given as the k. So that I am denoting with a point. Function value denoting with k. Right. And when x is greater than a, function is given by the same piece, y is equal to f of x. It is like this. Sorry, y is equal to g of x. It is like this. Now you observe that in our style, domain is taken. This is the point at x is equal to a. So limit of f of x as x tends to a minus the left limit of f of x at a I am evaluating, means in the left side of a, the function is given by the formula g of x. That g of x I am evaluating, but from the graph of the function, that g of x left limit at a is given by that height L. Therefore, this left limit is L. And the limit of f of x as x tends to a plus in the right side of a. So that is x is approaching to a through the right side of a. Then in the right side of a, function is given by the g of x again. So that g of x formula is again L. So here, for the function f of x, at a, left limit is L, right limit is also L. Implies two-sided limit extends to a exists, and its value is nothing but the L. So at x is equal to a, left limit exists, right limit exists, both of them are equal. Therefore, its two-sided limit also exists, which is the common value of left and right limits, which is L. But this is not equal to k, which is the value of the function. So for this function at a, left limit exists, right limit exists, both of them are equal, means both sided limit exists, but the limit of the function is not equal to the value of the function. Therefore, it is a discontinuous at x is equal to a. This type of discontinuity is called removable discontinuity. Why it is removable? Because just by redefining the function value at x is equal to a, instead of k, take its value L, then the function will become continuous. Just by changing the value of the function at only the point a, you can make the function to become continuous. Therefore, it is called removable discontinuity. And continuity itself is failed at a here. Once a continuity is failed, so definitely continuity means that there is no break in its graph. But here in this graph, we got the break at x is equal to a. Function got the break. Therefore, it is a discontinuous. So discontinuous implies always non-differentiability. A function is a discontinuous. You need not check anything. Automatically, it is non-differentiability. Right? So this is exactly the point from here. This is one of the case. Similarly, let us discuss one more case. Suppose f of x is equal to g of x when x is less than a, and h of x when x is greater than or equal to a. Means left side of a is given by one piece, right side of a is given by some other piece. So fx piecewise, if we write like this, when x is less than a, it's given by g of x. So x-axis at x is equal to a, the function piece is given by like this, and at x is equal to a, function value is taking its right side piece. Therefore, for the left side piece, I kept it 0 there, whole there. So that is y is equal to g of x. If x is greater than or equal to a, given by the h of x. So this is exactly y is equal to h of x. Now, the interval is taken like this at x is equal to a. Now I am calculating limit of the f of x as x tends to a minus. Yet a in the left side is same as x is approaching to a through the left side of a is same as in the left side of a, it is given by the piece g of x. So the limit of this g of x as x tends to a. So from the diagram that becomes L1. Therefore, this limit is L1. Then limit as x tends to a plus of f of x. That is the right limit at x is equal to a. So right side of a is given by the formula h of x. That h of x formula is taken here. So therefore, this value will be L2 from the diagram. So therefore, this limit is L2. And you see that L1 is not equal to L2. If L1 is not equal to L2, means that x is equal to a, left limit is L1, right limit is L2, and here in this problem, right limit itself is the value of the function, which is L2. So overall, left limit exists, right limit exists, but the not equal. Therefore, limit of fx as x tends to a, both sided limit does not exist. Though the individual left limit, right limit at x is equal to a exists, both sided limit does not exist here. So this type of discontinuity is called jump discontinuity. So here you see the graph. Graph is taken a jump there. It is called jump discontinuity. Again, continuity implies there is no break in its graph. But here in this graph at x is equal to a, we got the break. Because therefore it is discontinuous. So always discontinuity implies non-differentiability. Again, this function is non. Do watch, like, share, and subscribe these videos to get its corresponding problems. Right? See you. Good luck.